All right, this will be the first in a series of 3 lectures on reverse engineering machine code, so introducing you to the sort of basics of reverse engineering. In this particular lecture, we're going to talk about some of the standard calling conventions that you'll encounter, how to recognize conditional logic in low-level assembly code, so if then else type constructs, for loops, etc. And also talk about some of the tools of the trade that you'll be using in this course. So to start with, talk a little bit about the standard entry sequence to functions. So when a typical function is called, there's a few basic things that are done on entry point. First is that it's going to save the old base pointer. This is all about setting up a new stack frame for the function that's being called. So it saves the old base pointer, sets the new stack base pointer, so it's basically taking the top of the stack, what's in ESP, moving that into EBP. And then it may or may not allocate space for variables depending on what the function is designed to do. So you'll either see that function, the sequence at the top, or in the second example here, there's the enter call or enter instruction. And the enter instruction just basically does the same thing as push EBP, move EBP, ESP. So the standard exit sequence is just the flip-flop of the above. You're going to then set the stack pointer to the base pointer, so you're reloading the old stack pointer when the function was called. Then you're going to pop EBP off the stack. So remember at the beginning, when we entered the function, we saved it, and you'll deallocate any space that was allocated in return. Similar to the enter assembly statement, we also have a leave statement, and that does the same thing as move ESP EBP and pop EBP. All right. In addition to the standard entry-exit conventions, we also have different calling conventions that you'll encounter. These are typically decided by the compiler writers. You have this cdecl, standard call, fast call, a lot of different implementations that you'll encounter. But the importance of understanding, or at least being familiar with these, is that it will help you more quickly figure out what variables are the arguments that are going into the function, and whether it's the caller or callee that's responsible for cleaning up data. So cdecl, this is used by GCC and the GNU libraries. Windows is mostly standard call, and then there's fast call, and we'll talk about each of these in more detail. With the cdecl, you have your parameters. When you get ready to call a function, these are going to be passed right to left. So in your source code, right to left, that is. And so you'll see these being pushed onto the stack leading up to the call. Some of the registers are not preserved, EAX, ECX, and EDX. And the return value from the functions are typically returned in EAX. And so often, after a call, a cdecl call, you may see, if it's just testing to see whether or not it's 0, you may see it like a test EAX, EAX statement. And in that, it's inspecting what's in the EAX register, which is the return value. Also, with cdecl, it's the caller that's responsible for performing cleanup. So if it's pushing things onto the stack for that call, it's up to the caller to also clean that up. The standard call is basically the same thing as cdecl. The main difference is that now it's the callee that's going to clean up the stack. And in the previous lecture, you may recall the return immediate instruction, where it's like it's popping a certain number of elements off the stack. When you see that, it's a good indicator that it's a standard call that's being made. And then we have the fast call. In the fast call, parameters are passed in registers. So as the name implies, this is a little bit more efficient because there's not an extra step of pushing data onto the stack. It's already in the registers, and so the function call can just be made in those registers and then used in that function as needed. And so you'll see this with Microsoft Visual C++ and GCC can also use fast call. And so Typically, you have the first arg in ECX, the second in EDX, and then the remainder of the arguments are from right to left. So to just walk you through detail what a CDECL function call looks like. First step, pushing all those parameters onto the stack. These are all your arguments, and these are going to be right to left. Then the function call itself is going to be made. The function's called, the first thing that's going to happen is you're going to see the base pointer register saved and then updated to create that new stack frame. And then registers that are going to be used in this function will be saved, and so they'll just be pushed onto the stack. And then if there's local variables that were in the source code, we'll have space allocated. And by allocation here, this isn't calling malloc. This is actually just allocating space in the stack. So you're going to see some integer value subtracted from the ESP or stack pointer to create that space. And so when you see EBP minus some value, because recall that the stack goes downward, it's accessing those local variables. Whereas if EBP plus some value, it's going to be accessing the parameters. So after the local variable allocation, then the actual function itself runs. Then any local storage that made will be released. So in this case, we'll be adding to the stack pointer. Restore the save registers, restore the base pointer, return to the caller, and then the caller cleans up the parameters. For the standard call, just to walk through that, you'll see that this is pretty much the same, very similar to CDECL. You're pushing the parameters in the stack, calling the function, saving base pointer, saving the registers, allocating space for local variables, executing the function, releasing local storage, restoring and save registers, restoring EBP, and then here's the main difference, cleaning up the parameters. So it's going to be anything that was pushed onto the stack here will then be cleaned up, and then it returns to the caller. Here are some others that you may come across. Pascal calling convention. See this in older versions of Windows, where the parameters are actually passed left to right. There's the syscall, where the parameter size is passed in the AL, which is the low byte of EAX. Save call, and this call. We won't talk in too much detail about these others. Okay, so moving on to some control statements. One of the core things that you need to understand, reversing the code is being able to identify and understand conditional logic, so you get a sense of, okay, what's going on in this function. So we're going to talk about if-else statements, switch, for, and while loops. So here's some basic source code. We just have a main function. It's calling a do something, and then it's going to check to see, is the parameter that was passed in greater than 0? If so, then it will print out greater than 0. Otherwise, we're going to print out not greater than 0. So this is a snapshot. This is actually, we're using Ollie debug, which is a tool I'll talk about a little bit later. But this is a disassembly of that code. Just to kind of give you a feeling for what you're looking at here. On the very far left, these are virtual addresses, the 0040160. Those are all just addresses in memory. The next column here, where you see a bunch of hex bytes, these are the actual opcodes and operands, so the binary code that's in the actual executable file. These correspond to the assembly mnemonics and instructions that you see here in this third column. And in the fourth column are just some things that the disassembler, in this case Ollie debug, is helping you out with by saying, hey, this is the string, and it's being passed to the printf function. So if we go down here in this function and to take a look at what's going on, you'll see at address 401078, we see this comparison. It's comparing EBP plus 8 and 0. So EBP plus 8, we know this is going to be accessing a parameter that was passed in because, again, think about where EBP is going to be pointing. It's the base pointer. So if we go EBP plus 4, that's going to be the return address. And then EBP plus 8 is going to be an argument that was passed on the stack. So this corresponds to that IVE variable that we saw in the source code. So it's comparing it to 0. And then we have a conditional jump if less than or equal. It's a short jump, which just means that it's this is a relative offset. So it's jumping to 40108D if that condition's met. So if you look down at what's at 40108D, you'll see, okay, it's printing out a statement not greater than 0, which makes sense because, obviously if it's less than or equal to 0, then it's not greater than it. If that condition is false, then you just go straight to the next instruction, which in this case is pushing greater than 0. Now the jump instruction, it's when the compare instruction executes, it's going to be setting flags, because recall that compare is performing a subtract operation, and there'll be flags, the eFlags register, where flags will be set based on the result of that computation. And so the conditional jump statement is going to be checking those flags to determine whether it's less than or equal. So that's a very basic if-else type construct that you'll see in code. Just basically compare followed by a conditional jump, and you'll have, in this case, there's just two different paths through that. All right, so now let's look at the switch statement. Here we have, again, the same two basic functions. We have case 0 and 1. It's going to print out 0 or 1. Case 2 will print out 2, and the default case is to simply break and not print anything. Okay, again, so here we have the disassembly. And let's zoom down here to 401078. Here again we see the parameter that was passed into the function. It's being assigned to the EAX register. And then now we're moving EAX into EBP minus 4. So this is going to be some local variable that we had allocated space for. And it's comparing initially to 0. Now the next jump you see jump if less than, and then it goes down to this AE. So back in our source code, we didn't really have a condition for less than 0. We're specifically checking for 0, 1, and 2. But naturally, less than 0, that's going to fall into the default case, right? So that should just break and do nothing. And that's, if you follow the address, if you go down to 4010AE, you see that it's basically skipping over this whole series of comparisons. Okay, so let's go down. So then if we pass 0 or 1 and it's not going to take that first jump, then it compares it to see, okay, is it less than or equal to 1? We've already covered the case where it's less than 0. So this is basically checking 0 or 1. If that's true, we're jumping to 41092. And as we see down here, that corresponds to you see it's pushing the string 0 or 1 onto the stack and then calling printf. Okay, so then if we continue on, so let's say that it didn't take that, it's comparing it to 2. If that's true, then it goes to the 4010A1 address. And there you see it's pushing the string for 2 onto the stack and then calling printf. And Otherwise, you have, if that falls through, then we also have this unconditional jump statement. JMP will always be taken when executed, so there's no condition there. And so essentially, if it didn't pass that, then it's going to go down to that AE address, which is the same one that you saw in the very first case, branch to, if it was less than 0. So it goes down to AE and then goes from there. One thing you'll also see if you just continue to follow the logic, in the case of the first printf, you see it adding ESP. So that's just cleaning up the stack from the variable that was pushed to printf, and then you also see it unconditionally jump down to AE to skip over that next printf. So this is what a switch statement looks like. You're going to have, again, a series of these comparisons, and then you'll see it all kind of converge at one exit point. Okay, so now we have the for statement. Again, we're using the same basic function setup here. Called the do something with the parameter, and then we're essentially looping. So if you pass 10 in this case, it's going to loop through here from 10 all the way down to 0, and then as long as it's greater than 0, and then it's going to exit from the loop. Okay, so Ollie helps us out a little bit here in terms of identifying the loop. You'll see this black bar in the third column, and this is just essentially indicating that we have, helps you identify that there's a loop and points out that condition. So but if you look at right above the loop, we've got this jump short down to 401083. And so you'll notice that that's skipping over the initial, like the subtract operation, right? Which makes sense because in a for loop, you're not going to be performing that operation that's in the, the third parameter, essentially, of the for statement. So it initially jumps down, just checks to see, hey, is this, if it's less than or equal to 0, then it will immediately jump out of the loop. But if it isn't, so if it's greater than 0, then you see it's going to basically print that string. You see it pushing. There's two arguments in this case to printf. ECX receives the current value of I, and that gets pushed, followed by the format string to printf. Then it hits the unconditional jump, which takes us back up to 7a, and now it's going to subtract 1, and then it's updating I by moving. So they're basically moving the I into EAX, subtracting 1 EAX, and then moving EAX back into the I variable, which is on the stack. And then it does a comparison again, and it'll just continue in that loop until it's 0. Right. And now we'll look at the while loop. Again, doing a similar thing to what we just saw in the for loop. The main difference here is just, instead of, we're not jumping into this loop like we saw in the for, here it just enters, and the first thing is the compare. It'll branch out of the loop if it's less than or equal to 0, otherwise it starts executing this code. You see the subtraction down here at 401092, and then it just jumps back up, and it's just going to stay in loop similar to the other one until the condition is satisfied. So the difference between the while and the for is somewhat subtle, and it's up to the compiler. It's up to the compiler ultimately, like how it's going to generate the code. So what the code's going to ultimately look like. But those are some basic patterns that you'll see. Now, some of the variables, you may be wondering, well, how do you tell the difference between whether this variable is signed or unsigned? Well, there's actually different instructions that are used. So with the multiply and divide, for example, you have signed or unsigned, likewise for the division. And also, you can tell by the conditional jumps that are used. So if we look at this chart here, at the top we have the instruction mnemonics that are used for unsigned conditional jumps, and then down below we have the set of conditional jumps that are used for signed statements. also in this chart, you can see what flags are actually being checked. Recall these flags are, again, in the eFlags register. And they're set and unset as a side effect of other instructions, like compare, for example. The third column here just has a more verbose description of what the jump stands for. All right, so now you have general feel of sort of the basics of looking at common code constructs. We'll talk a little bit more about the different tools that you'll actually be using to do your reverse engineering. And the three big ones are disassemblers, decompilers, and debuggers. The first two, disassemblers and decompilers, these are used for what's called static code analysis. So it's static because you're not actually running the program. These tools are going to take as input some executable program. They'll do analysis over the code. There's two main disassembly type algorithms. One's called a linear sweep disassembler, and the other is called a recursive traversal. If you do some Googling and searching on the outside, you can kind of read more detail about the algorithms, but the more advanced disassembler is going to do a recursive traversal, and that's where it's going to, as it's disassembling, it's going to be following, all the branches that encounters a jump, will take both paths that could come out of that jump and just sort of recursively disassemble it until it can't disassemble anymore. And the disassembler, there's two main things it has to take into account. There's the file format, and so under Windows you'll see it's called the portable executable or common object file format, so PECOF, and under Linux is ELF, executable linker format. And so these are the two different file formats, and each of these file formats has the header. The header has information about how the code's laid out and whatnot. So the disassembler will parse that header, figures out where the entry point is to the program, and then it will run its disassembly algorithms to do that analysis. The decompiler does further analysis on that disassembled code. And so the decompiler is going to try to take the instructions all the way to a higher level source code representation, usually C code. And last, we have the debugger. The debugger is a type of dynamic program analysis, and this is because you're actually now running the code, but you're doing this in real time and you're stepping through it. So you're seeing the code execute right on the processor, and you can either single step and set breakpoints, and we'll talk all about that here in a little bit. So as I explained before, disassemblers, you're going from machine code to instructions. It's going to take the bytes that you see here in this middle column and turn those into the assembly mnemonics. Now the Intel manual that I referenced in the previous lecture, when you go through there and you look at the different instructions, you'll see all the different opcodes, and you may be surprised. Like the move instruction, for example, has many different opcodes. It's not just always like 8B as you see here. Some of them are longer, and different opcodes indicate that in this case this is just a move EVP ESP, but there's some opcodes may be move particular register and then take some 4-byte argument if you're moving an immediate value, for example. And so it may be worth your time to kind of take a browse through some of the instructions just so you kind of get a feel for how to read the manual, understand what the opcodes look like, and then how that translates to these different mnemonics. Okay, so with the decompiler, like I said, these are trying to convert instructions or byte codes, in the case of like a Java bytecode, to a higher level language. We say here that good decompilers are implemented via a P-code analysis. So just think of that as doing an analysis on an intermediate language. And this is because a good disassembler is going to support many different architectures out of necessity. You have ARM, you have Intel, you have different variants of Intel. So a disassembler's got to understand all those low-level details, and they're very architecture specific. But when you're decompiling code, you really care much less. You don't really care at all, for the most part, about the low-level architecture-specific things to some extent. What you care more about are recognizing structure in the code, similar to what you saw earlier when we were, when I was explaining about the if constructs and things like that. You're looking for those because then you can map that into C code. So if all that analysis though can be done over a common, in this case it was called a P code, and so you'd have a step that would essentially, in the decompiler, take the assembly mnemonics that were disassembled by the disassembler, convert those into P code, and then do the analysis on the P code to then convert it into a higher level C-like language. All right, and debuggers, you have two main types of debuggers. You have user mode and kernel mode debuggers. There's also hardware debuggers like in-circuit emulators. Won't talk too much about that in this course. Those are where you actually have a piece of hardware sitting between the processor and the motherboard, so you're like literally intercepting everything. Those are much more expensive and specialized tools to work with. But in software, you have the user mode and kernel mode. User mode, of course, is just debugging applications. Kernel mode, it's going to be running at, of course, a higher privilege level and allow you to debug the actual operating system itself. Almost all debuggers are going to have these set of features, basically creating and attaching to a process to debug, setting, clearing breakpoints, stepping into functions or stepping over functions, and likewise tracing into and over. So we talk about breakpoints. There's different types of breakpoints that you can set. A very common type is a software breakpoint. In a debugger, when you set a software breakpoint on the IA32 architecture, it's going to overwrite the byte that you told to set a breakpoint on with this hex CC opcode, which corresponds to int3, it's the instruction mnemonic. So it's going to overwrite that, and then when the debugger encounters that, it generates an interrupt. The debugger catches that exception, so that's how it breaks into your debugger and halts the execution of the program. And then, of course, it's going to replace that byte with what it originally was. So you, the user, you don't usually see that, but that's actually what's happening behind the scenes. There's memory breakpoints, so you can set a breakpoint on this, specific address, or setting a breakpoint on access to memory. The hardware debug registers can be used to do just that. And so with these, you set a particular address and a type of breakpoint that you want to be triggered by, and then it will, when that condition is satisfied, it will break into your debugger. Tracing, for this is where we're actually going to be recording instructions and the execution context. So as the program is running, it's basically recording everything that's happening. And this way you can kind of get a feel, you can combine this with your static analysis, like that you would get from your disassembler and whatnot, with an actual running of the program. And this often helps, especially when there's a lot of computed jumps and things that get to be harder to identify and reason about from a pure static analysis perspective. And then when we talk about stepping into, just as the name implies, if you want to actually see what a function does, you step into that function. If you don't care what that function does, you just want to skip over it, you step over it. And when you step over a function, it's similar to a software breakpoint because it actually sets the CC byte on the instruction wherever the return address is. So basically, then the program runs, then it hits that CC and it breaks back into your debugger. So it gives the illusion that, okay, you're just stepping over that function. That's because you're not actually tracing into everything that was called by that function. So talking about some more specific tools now, there's GDB. I mean, if you use Linux at all, you're familiar with this tool. This is a command line tool. There are some GUI wrappers for GDB, and it actually isn't just for Linux. There's Windows support as well, various architectures, but very powerful tool. A lot of good help references out there that will help you with commands and whatnot. So this just gives you a little simple breakpoint tutorial. Here we have a hello world program, so we load that up into GDB. We pass the command, the disassemble command, to main. So this is just disassembling the main function is all that's doing. And now we're going to set a breakpoint at 8048249. So if we look back over here, that's that move instruction. So then we set the breakpoint, then we run, encounters that, hits the break. We take a look at what's at the address, and you'll see the 809FD48. That's a data item that's being moved in. So that's basically what's being printed, and so that's the command in GDB to actually show what's at that address. So we see, okay, it's printing hello world. Then we issue the continue command, which is just the C, and then the program runs, so it actually prints hello world. That's essentially your console, and then we queue to quit. Ollie debug. This is a very popular disassembler debugger. Been around for many years. There's the first version was in the early 2000s, and then the author did a big rewrite with version 2.0, which came out just a few years ago. Again, it's a disassembler and a debugger. Has able to open, attach, detach, kill processes. You have a lot of nice views here. If you want to look at the call stack, breakpoints, executable modules that are loaded into the address space, you can tell it's a very powerful tool and free, so you can just go and download it online. In 2.0, the interface changed a little bit, so you can kind of see a few differences. Some of the things you may see missing here. So for the code analysis, it does a lot of nice features. Like you see in the right, it's pointing out the arguments and what the values are that are being passed into, like in this case, the malloc function. So a lot of that's helpful. It just speeds up your analysis. There's just-in-time debugging, so basically if there's a fatal error that occurs, then it's going to pop into the debugger. And you can also write plugins for it. So if you want to programmatically do something, there's a lot of powerful things you can do, and really the reverse engineering community has developed quite a few plugins for this tool. So if you search around online, you should be able to find plugins and different add-ons that people have written for Ollie and test them out. So to set a breakpoint, it's pretty simple. You just hit F2. You see that it highlights the address in red, so it's very visible where the breakpoint is. If you want to resume execution, you just hit F9, continue executing. We see, if you go back and forth, initially it broke here at the beginning of the function, where it's highlighted in gray. We hit resume execution, then you can see it ran until it hit the next breakpoint here. There's the stack view. So if you look in the bottom right corner here, you can see what's on the stack. If you look at the stack over in the right column, look at ESP, it's at 0012 FEDC. And so you can see down the right, we're looking in that range of where the stack is. EBP is pointing to FF28, so you can see that the little black bar there in the second column of the bottom right section where you see the stack, that's basically showing you the stack frame. So stepping, if you want to step into, you just use F7. So you're stepping in the function. So I'm just going to go to the next instruction, basically. If there's not a call, it's just going to go to the next instruction. Here, there's a call, so we hit F7. Then it actually stepped into it, so it takes that call and then takes us into the function body there. If we were to step over it, then it's just going to skip it and go to the next instruction. You can also patch code with it. This is really handy, especially if you're trying to patch a program and you want to test to make sure your patch worked. You can test it directly from Ollie, which is really handy. So let's say you wanted to change from over here. We have this invalid license key or valid license key. So you want to make it so it always says you have a valid license key in this demo program. So that's the goal. So we're just going to double click on that jump. Pulls up this window with the assembly, and so we can change that to whatever we want. So now we're going to, in this case, is changing the jump address to go to 40BA13. You could also just always have it go there if you wanted as well. You could change it to JMP potentially. Hit assemble, and you see that, okay, now it just changed the code. And so now it will always take that jump. There's a way of, if you want to view all the patches that you've made, you can click on, there's a patch window, this little / icon. It'll show you, so if you look in the bottom of the screen there, you can see we have an active patch. So you can make it inactive too if you want to undo it. If you want to actually write this out to the binary, so to make it permanent, then you just do this copy to executable, all modifications, and slightly different in Ollie Debug 2.0. And again, you click on it, click copy, you see the window that comes up there, and then you're just going to save the file to the new executable. Give it a name, so it's a little different, and that's it. So pretty straightforward. All right, so now we're talking about IDA. IDA is probably, I would say it's without a doubt, most popular and common disassembler that's used professionally. There's also a commercial debugger and a pretty powerful decompiler as well. Also on their website, you'll find a freeware and a demo version. The demo version is perfectly fine. That's one of the reasons why we picked IA32 for this class, because the demo version works for that, so you can download it for the latest version of it, and it's pretty much full functional. There's a lot of things that you can't save the database, and there's things you can't write compiled plugins for, and there's a few other there's several limitations for the demo version, but if you just want to get a feel and test it out, it's a great product and tool to use. Used to be managed by a company called Data Rescue, and now it's a Hexray's product. So if you go to Hexray's website, that's where you'll find it. And your school may or may not have license to the full version, in which case you'll be able to play around with a variety of architectures because it supports quite a few. But the decompiler is sold separately and is fairly expensive. So this is a little picture of IDA. The window's a little bit shrunken down just due to space limitations here, but just by looking at this, you can see how useful this kind of view is, where it's showing you whether a jump, for example, the red would be if it's not taking, green if it is, and so very handy for getting, if you want to conceptualize the control flow within a given function. This graph view is very useful for that. There's all sorts of other features, like you could spend days talking about the features of IDA, so we'll keep moving along here. So these are some of the most common commands and things you may want to do. I'm not going to read these all off because I also have these slides posted so you can reference these. But these are just some of the most common things that you'll want to do. And it is interactive, so that's really the use things. If you see a jump to an address, you can just double click on it and it'll take you to that address in the binary. So lots of very useful things to do. The cross-referencing, that's the one thing I do want to highlight. When you are reversing, the cross-references are extremely useful, because what's likely to happen is you may see a string or some data item that jumps out at you as, hey, I care about this. Where is this reference in the program? Well, if you display the cross-references, it'll show you all of the locations in the program where that memory address is referenced. And so that's extremely powerful, because you just simply click on those cross-references and it immediately takes you to where you are in the code that you care about. And that's half the battle with reversing is just sifting through. There's a, and even the simple programs, there's thousands of instructions, and so finding the important relevant sections of code that you actually want to spend the time to reverse engineer, that's part of the sort of art of getting good at reverse engineering is understanding that and developing techniques and skills to quickly zero in on what it is that you care about so you don't waste time reverse engineering just random code that isn't relevant. So this just shows, changing some of the config if you want to be able to do patching, similar to what we went through with OllyDebug. And to give you a feel for what a decompiler looks like, it's going to take, this is an example of the Hexer's decompiler. On the right here, we actually see they not only labeled the calling conventions, you see the cdecal, they have the name of the function, arguments. And granted, this is a very simple function, so it's pretty readable. More complex functions, of course, aren't going to be as pretty and readable, but it is very powerful and can save quite a bit of time reversing. Obfuscated code this isn't going to be that useful for because it probably won't be able to do a very accurate job. But for some simple functions, you can look at the decompiler and get a good feel for what it's doing. Another very powerful debugger and also free for Windows is WinDebug, or some people call it WinBag. Very powerful. There's a huge set of commands that you can issue. Lots of good documentation online for how to use it. And you can also do things programmatically with WinDebug. So very useful, especially if you're debugging Windows, anything within Windows where you need to be familiar with Windows data structures and whatnot. It's quite handy for that because it's very easy to load all the symbols and whatnot into the debugger to give you meaningful and pretty names like you see here where it says, like in this case, NTFS test filter, for example, is just an example. And that concludes part one. Again, if you have any questions or comments, just send it to, you can email us or feel free to comment on the Google Hangout site. So